Hello, we're going to continue on the chapter on integration by looking today at the definite integral. Okay, we had a little look at indefinite integrals last time, so today we're going to look at the definite integral. Okay, so what are we talking about? Well, let's start with a question. Okay, and in fact it's a very, very easy question that we'll start with today. So we'll assume that a car is going to travel at a constant speed, 60 miles an hour, and it's going to drive for 2 hours, and ask how far has it travelled. Okay, and before we answer the very easy question, let's just look at this graphically. Okay, so the y-axis here we have miles per hour, the x-axis is the hours, the time travelled. And so we have 60 miles an hour, the horizontal line, for a total of 2 hours. And so of course the answer to that question is very easy, 60 times by 2, so we travelled 120 miles. But we can also notice that if we look at this graph, the shaded area there, the area underneath that line, well, it's a rectangle. Its width is 2, its height is 60, so in fact the area there is 120 miles. 120 units, 120 miles. So we're getting this relationship between the function and the area underneath the curve. Okay, let's ask another, well, slightly more difficult question, not much. So now we're going to assume that the car travels at 60 miles an hour for 2 hours, then instantly, which I appreciate isn't very realistic, changes direction and goes 20 miles an hour back the opposite way. Okay, and it's going to do that for 1 hour. Okay, so we take the picture again. So again, we have the 60 miles an hour for 2 hours. We have the 20 miles an hour, but in the opposite direction. So we're going to give a negative 20 miles an hour here for 1 more hour. And now we're going to ask the question, how far are we from where we started? And notice this isn't quite the same as asking how far have we travelled. Okay, because we've travelled some of the distance back again, so we're asking for how far are we from where we started, and mathematically we call that displacement. Okay, what is our displacement? Well, 60 times by 2, how far sort of out we went, 20 times by 1 is how far back we came, and so we get 100 miles. Okay, and now if we think about this as areas, well, this area is 120, this area is below the curve is 20, and we can think of that as kind of negative 20 because it's below the curve, so we get 120 minus 20 is 100 miles. Okay, and that's going to help us think about the definite integral and what that gives us. Okay, so I'll have one more question, and again it's not entirely realistic, but it's just helping us think. So a car starts at 10 miles an hour and accelerates constantly, so it's got this nice smooth constant acceleration, and after 5 hours it's going to go at 20 miles an hour. Okay, so it's not going very fast and somehow it's accelerating very accurately for a whole 5 hours. Okay, and graphically this looks like this. Okay, it starts at 10 miles an hour, ends at 20 miles an hour, and we're going for 5 hours. Well, now how far has it travelled? What's its displacement? Notice those are the same now because we're going in one direction. Well, there's a couple ways to think about this. One is, well, the average speed it's going to travel would be 15 miles an hour. And 15 miles an hour and 15 hours would be 75. But let's think about this in terms of this area. Remember, we seem to think that the area under the curve was giving us the distance travelled. Okay, and to find the area of the shape, this is a trapezoid. We can take the average of the two heights, so the height at this end plus the height of this end divided by 2, multiplied by the width. So that's 10 plus 20 over 2, multiplied by the width of 5, so that gives 75 miles, and that was what I sort of intuitively thought it was going to be. Okay, so we've got the area under that curve to be 75, therefore we've travelled 75 miles. Okay, so let's get into the definition. Okay, so we're talking about the definite integral and total signed area. That signed is important, taking into account the negatives and positives. Okay, so we have some function y equals f of x, and it's defined on a closed interval from a to b. And the total signed area from a to b under f is the area under the function that's above the x-axis, and then we subtract the area above the function and under the x-axis. Okay, that gives us the total signed area, and the definite integral of that function on a to b has a total signed area and is denoted by this. Okay, so it's the integral from a to b of f of x dx, where a and b equal the bounds of integration. Okay, so last time we saw the indefinite integral, which didn't have these bounds. Now the definite integral has these bounds and gives us a numerical value. Okay, just as we saw previously, there's a few definitions or properties we can see of the definite integral. We'll justify one of these in a second. Some of these we can think of just in terms of areas, which is very straightforward. So the first one says if we integrate from a to a of the function, we just get 0. And that's very easy. If you just draw a picture and think about integrating from a to a, it's not going to have any area, therefore the definite integral will be 0. Number 2 we'll look at in just a second. Number 3 says that if we switch the limits of integration, we get the negative. And numbers 4 and 5 are similar to things we saw with the indefinite integrals, that if we add or subtract two functions within the integral, we can add or subtract them and take separate integrals. And the final one, number 5, says if we have a constant multiplied by the function, we can take that constant outside. Okay, so I mentioned we'll look at number 2. So let's justify that. Okay, so this says we can integrate from a to b function and integrate from b to c and add those, and that will be the same as simply integrating from a to c. Okay, and that's fairly straightforward to justify as long as we have this picture. Okay, so we have some function, whatever it might be, this f of x. Okay, I'm thinking about integrating from a to b, we get this area. If we integrate from b to c, we get this area. And of course, if we add those two areas up, well, it's the same as getting the integral from a to c. Okay, so that's that rule justified. Okay, so we'll finish off with an example of how we can use this definite integral. Okay, so consider this diagram. It's fairly straightforward, all nice straight lines. What is the integral from 0 to 4 of this function? Okay, so what it's really asking is, what is the area underneath that curve from 0 to 4? Well, it's triangle. We can use half base times height. So its base is 4, its height is 4. So we have 4 times 4 over 2, so the area of that is 8, which is the definite integral. Let's now integrate from 0 to 6. And actually there's a couple of ways of doing this. We can just consider this as one big triangle. Because we'd already gone from 0 to 4, I guess I thought of this as two separate triangles. So from 0 to 4, we get half base times height. From 4 to 6, we get 1 half base times height. The base is just 2 now. And so we get 8 plus 4 is 12. I'd say you could also think of this as just one big triangle. Okay, the base is 6, the height is 4. So we'd get 4 times 6 over 2, which would also be 12. Two different ways of thinking about it. So we want to integrate from 9 to 10 now. Okay, and in fact this is an easier shape. This is just a rectangle. Its width is 1, its height is 6, or like negative 6. But recall our rule that says if we're below the axis, this gives us a negative. So the area here is 6, but because we're integrating, we're below the axis, we get a negative 6 as the value of the integral. Okay, and finally, suppose we want to integrate the whole thing. Suppose we want to integrate from 0 to 10. Okay, well again, we can break it into, well I guess I broke it into 4 pieces. Okay, the first piece we've already seen, 4 times 4 divided by 2, that triangle. Second piece, we've already seen again, 4 times 2 over 2 is that triangle. But then we subtract the last 2 pieces, because they're below the axis. So the third triangle goes from 6 to 9, so its width is 3, and its height is 6. So we get 3 times 6 over 2, and we subtract that, and the final one is 1 times 6 that we've already seen. So that integral gives us negative 2, and if you like, that's kind of the net area. We have slightly more below the axis than above it, and so the integral there is negative 2. Okay, we'll see a lot more on the definite integrals we're moving along, but that's about it for now.